Hey everyone, Sean here for Lambda School, and in this video I wanted to go over problem flow, or kind of my recommendation for how you might want to actually go about solving a problem, and I'm going to showcase that through the flow that I prefer to use when working on an interview problem or on a whiteboard problem. And in this example, we're going to use the shifted binary search problem that you all have been receiving as part of the HackerRank assessment. So I'm not really going to go into details as to what the problem is. I'm assuming you've all done it before. So let's just launch into it. So this problem asks us to perform a shifted binary search, and because of the fact that the title of the problem says binary search in it, that makes me immediately think of, well, how can we use binary search in order to solve this problem? Right, so that makes me immediately kind of recall the binary search algorithm, which has us continually looking for a midpoint element, searching for the midpoint element in an array, in a sorted array of elements, finding the midpoint, and then once we compare the midpoint element against a target element that we're looking for, that tells us whether we can eliminate the left subarray or the right subarray. So on each iteration, we are successively splitting the array in half each time in order to get us a very efficient logarithmic runtime. So the thing with binary search, the binary search algorithm, is that it requires us to have a sorted array, right? Binary search acts on a sorted array. That's how we can do the whole checking against the midpoint thing in the first place. The caveat with this particular problem is that our input is not entirely sorted, right? So our input might look something like this. But if we go ahead and look at this input and notice something about it, what we see is that because it's rotated input, as in we basically started off with an entirely sorted array, picked a random index, and then went from the beginning of that array to the random index, took all of that and put it all in the back, right? So it's like we took 2 through 17, which normally would be at the front of the array, and we just like took all those elements and just threw them into the back of the array, right? Other than that, everything is entirely sorted, right? All the elements from 2 to 17 are sorted, and then all the elements from 19 to 49 are sorted. So if we're being asked to do some kind of binary search on input like this, kind of my immediate first thought is, well, okay, so there's 2 halves here. Can we do 2 separate binary searches, one on each sorted half, right? We could do a binary search on this subarray, and we could do a binary search on this subarray. And since both of those subarrays are entirely sorted, binary search would work. So that would be kind of my first inkling, which would be, let's binary search both sorted halves. Okay, so if we're opting to do that, if we want to binary search both halves, then that means in this given input array, we need to figure out where those 2 halves are located, right? So we need to find, for example, this, let's say we'll want to find the index where this 2 is, so that we know that this 2 here is the starting index for the right subarray, and then we know then that the left subarray will be starting at index 0 up to 2's index minus 1, up to this 49 here, right? So since we're thinking, hey, maybe let's opt to binary search both sorted halves, we'll need to figure out the index where the second subarray starts in order to do that. And then from there, let me move this over. At that point, we can go ahead and perform the binary search on both sorted halves. And then once we've binary searched both sorted halves, right? So like in the input over here, if we say we're looking for a target element of 33, well, in that case, we would expect that only one of the binary searches would return a valid index, right? In this case, the index for 33, right? The right binary search should not find anything because 33 is not in the right half. So if we're looking for 33, the left binary search will return index and the right binary search will return a -1, indicating that it did not find anything, which is totally fine. So let's work with that fact, and we'll say go ahead here and say that only one of the binary searches will return an index, and let's just say from that point, whichever one returns an index, simply return that index as our answer. And then there's also the edge case where, hey, perhaps let's say we're looking for 100 as our target, where 100 doesn't exist in either half because it just doesn't exist in the array. Well, if we're looking for 100, then both binary searches would not return anything. Both of them would return -1. And in that case, if we check for that specifically, then we can go ahead and say then that our shifted binary search function should return -1 because the target element is not in the array. So let's say if both return -1, then return -1. Okay. So that right here in comments here is what I will call, this is our what. This is what we're going to be doing. This is what we're going to be doing to solve this problem. And one very important thing that I want you to take away from this video is that we want to split up thinking about what we're going to do versus how we're going to do it, okay? So it's very important, or I highly recommend at the very beginning when you're thinking about the problem, again, we're just thinking of what we need to do. And at this point yet, I haven't concerned myself yet with how I'm actually going to do any of these things, right? Like if you look here, well, maybe I don't remember how to do a binary search and I might have to go ahead and figure that out. I don't know here in these comments, I haven't said anything about how I'm going to actually figure out the index, right? I just know that that needs to happen in order to follow through with this plan that I've laid out, the strategy that I've come up with But, you know, if we go ahead and actually execute all these steps that we've laid out in comments, then that should get us all the way there, right? So now at this point, we just need to figure out, given all these steps that we're going to do, the what of the problem, now we can go ahead and think of the how, right? So the how in this case will actually fill in the code. That's the actual how. So in response to all of these comments, we need to figure out, let's kind of just go down line by line. We need to figure out the index where the second subarray starts. Well, to do that, the first thing I'm going to do is I'm just going to go ahead, make a variable. I'm going to call it smallest index, right? Because the index that we get back here, this is going to be the index of actually the smallest element in the entire array. So I'm going to call it smallest index. And this variable is just going to hold the result of some function that I'm going to call find rotation point. This function is what's going to do the work of actually figuring out the index, okay? Right now, I'm just going to stub this out. I still don't know what this is going to do. I don't know what parameters it's going to take. I just know I'm going to throw all the logic that's going to be responsible for finding that index, that smallest index. I'm going to throw it all in this function. And I'm just going to keep going. From this point, we'll do the binary search on both halves. And for that, I'm going to say left index, which is going to be the result of whatever comes back from doing a binary search on the left half. I'm going to go ahead and store that in a variable called left index. And then similarly, we're going to have another one called right index, which is going to be the result of the binary search on the right subarray. Again, I don't have a binary search function yet. I haven't defined it yet. I haven't written it out yet. I don't even know what parameters it's going to take yet. I'm just going to stub these functions out. You can kind of think of this as like basically a bookmark, right? If you're bookmarking a web page, I'm leaving these here kind of as bookmarks to be like, hey, I know I need to come back to this. But right now, I'm just figuring out the how of just shifted binary search, right? And the logic related to finding the rotation point and the logic for binary search, well, yes, those are indeed needed and important for solving this problem. Those are distinct pieces of logic in and of themselves that we can just go ahead and relegate to a whole other function. We can have some other function worry about doing that stuff. And so I'm going to just stub that out, and then I'm going to come back to it later. Because right now I'm working just on shifted binary search, and I don't want to think too far outside of just this problem. So let's go ahead here and say, let's do that over here. We'll say if left index is not -1, that means it returns something, then we can return our left index. Similarly, we can do an if right index is not -1, then we can return the right index. So if either of those returns a non-1 value, we'll return that index because that'll be the answer we're looking for. And then finally, otherwise, we will just return -1 from this function, because if we get down here, then that means that both left index and right index are -1, so we'll return -1 there. Okay, so this is pretty much, believe it or not, going to be my code for the shifted binary search function, right? It's not done, but the structure of it is done. So the structure of it is done, even though, yes, these functions here still need to be implemented. But on the whole, I'm done thinking about the shifted binary search function for the most part, right? All the logic is here. Again, I don't have all the implementation details yet of these helper functions that I still need to work on, but the overall structure and logic of the shifted binary search function by itself is for the most part done. And the reason why I do it this way is because when we one of the things we want to try to achieve with our problem flow is we want to reduce mental overhead, okay? And we do that here. I'm doing that here with a couple of ways. One, again, being, it seems like this find rotation point logic is a distinct enough piece on its own that I'm just going to go ahead and think about this later, right? It's, again, needed for this function, but again, it's its own kind of distinct piece of logic. Same with the binary searches, right? Basically, I just kind of broke this problem down into, okay, if we find the rotation point and then we do 2 binary searches, that will give us what the answer we're looking for as far as this function's implementation is concerned. So really, it's important to, when you're working through a problem and going through your flow, that your flow kind of minimizes the amount of stuff you need to think about. Because when you can mentally minimize the amount of stuff you need to think about and kind of just focus right on the problem in front of you, that lowers mental overhead, and that makes it easier to solve just the problem in front of you, right? Again, I'm not worrying about what this function needs to do yet. I'm not worrying about how these binary searches are going to be implemented yet. I'm going to come back to those when I get there. Even though, well, now kind of is the time to get to one of them. So, right, so now, because at this point, we've pretty much finished the structure of our shifted binary search function, now we're going to move on to implementing these helper functions. So I'm going to go ahead and I'm going to do the binary search first, because hopefully we're at least somewhat familiar with binary search and we can knock out the easier helper function first. So with a binary search, the typical parameters that it takes, and here this would kind of be a situation where, well, if you've practiced binary search or you're relatively familiar with how a binary search works, at this point you can kind of just be like, oh, I remember from the last time I implemented a binary search, it takes in an array and a target and a left and a right. So we can go ahead and just hash out that function signature right there. But again, let's go back to thinking about the what of it before we think about the how, right? So binary search, typically we'll do it recursively, and when we're doing something recursively, we want to think about base cases. So one of the base cases first with a binary search is when left, and the left in this case will be the left boundary of the array, and right will be the right boundary of the array that we're searching through. We're progressively going to shift these boundaries closer and closer together until they essentially overlap. So one of the base cases for a binary search is when left is actually becomes greater than right because they've kind of overshot. And so in that case, in this case, when that happens, this is actually when we have gone through our entire array via the binary search and did not find what we're looking for. So let's say when left is greater than right, we'll return -1. So that's handling the case when the target we're looking for is not in the array. And then the other base case 2, is when array of midpoint matches the target element we're looking for. Let's say when that happens, we will go ahead and return mid, the index, because that tells us the index where the target is in our array. So those are our two base cases. And then what we'll do in order to actually move towards these base cases is we'll say so long as left is less than or equal to right, then we will, here, let me go ahead and structure it like this. We will calculate the midpoint between left and right. We will go ahead and check if array of the midpoint matches the target. If it does, then we've fallen into base case 2 and we can go ahead and return that. If not, so let's say if array mid is greater than our target, then we want to call binary search. We want to call it on the left subarray, because if the midpoint is greater than the element we're looking for, that means we can eliminate the right side of the array and we can throw all of those out, and we just then want to consider the left subarray. Conversely, on the other side, else if array mid is less than the target, then we want to call binary search on the right subarray. And then this will eventually get out of this loop to the point where, hey, if we end up back out here again, then that means that we're no longer in this left is less than or equal to right point, and that means we've gone through our entire array, at which point now we know that the target is not inside of the array, so we can go ahead and return -1. Okay, so that's a pretty complete picture of the what we're going to do. And in fact, I would say this does kind of stray pretty closely into how territory, because a lot of this looks way more like code than the comments I had in the first part. But anyway, so we can pretty much do a complete translation of this section of comments, the what, right into the how. So if left is less than or equal to right, we'll go ahead and calculate the midpoint. And with this particular formula I use, this is kind of another thing you just kind of memorize for when you need to go ahead and whip out a midpoint. Let's go ahead and do this check. If that matches the target, we're going to go ahead and return a mid. Otherwise, if array mid is greater than target, we will say return a recursive call to binary search with the same array, the same target, and then in order to actually limit the this binary search call to just the left subarray, we're going to keep the left boundary the same, but we need to go ahead and move the right boundary closer. And so in this case, we're going to call this with a right boundary of mid minus 1. So the element right to the left of this element here. So we've already considered this one, so we don't need to include it in our binary search call here. We can toss that one out as well. Over here, then we can say else if array mid is less than target, we'll return binary search on the right half. So again, same array, same target. Here it's going to be mid plus 1 with the same right boundary. Otherwise, we get out here, format this correctly. Otherwise, we get out here and we'll go ahead and return -1. Okay. So again, the important takeaway here, again, we separated our what and our how. Probably not as well as the first part, but it was a little more blurry because I've written binary searches so many times. But anyways, so we separate the what and the how, and with this kind of modular layout of sticking the binary search into its own helper function, right? We helped ourselves by kind of mentally relegating ourselves to just thinking about binary search, right? Like as we're working on binary search, we don't need to think at all about any details pertaining to the shifted binary search or this finding rotation point function, right? We're kind of mentally gatekeeping ourselves. We're mentally putting a fence around our brain to just have it think about binary search. And when you actually do that during a problem, that helps you just focus on the problem right in front of you. It makes thinking about it kind of more clear, so you get to think about it with a little bit more clarity. Another important aspect is that, well, we could actually go ahead and test this function just on its own, right? So we can go ahead and do a binary search right here. Let me throw that into an array. But again, because of the fact that we have the binary search logic within its own function, that makes it easy to test against. So if we go ahead and run this code, let's go ahead and look at the, doesn't have a debug out. Right. So we need, of course, the array target. Let's say we're looking for the 33, left of 0, and then let's do length of array -1 as the right boundary. Go ahead and run that again. See if that shows up in the debug output. Yeah, okay, so debug output, we get 11 over here, and let's make sure that's correct. So we start with 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 11. Yep, okay, so the 33 came back with index 11, which is correct, and then let's see what happens when we go ahead and give it an element that is not in the array. And here we're expecting a -1, and indeed we get a -1. Okay, so so that's a little bit of testing of our binary search function, which is handy now because we can be relatively certain that this logic, at least on its own, is correct. Okay, so with that out of the way, we can move on to the other function, the find rotation point. And thinking about what this function needs, it's going to need the array, and actually that's going to be all it will need, because we're assuming that it's going to receive an array that already has been rotated, so it's just going to find that index for us. And again, let's go back to thinking just about the what. Okay, so we also want to use some kind of modified binary search strategy in order to find this rotation point. So we're going to do things again like finding the midpoint of this array. And then now let's think about, so let's say we're going to use some sort of binary search here as well. So again, we know we'll want to figure out the midpoint element. But then the question becomes, what do we compare the midpoint element against, right? Because with our binary search function up here, we just compared the midpoint element against the target element. And then that told us pretty clearly, hey, if the midpoint element matches our target element, that just tells us right where the target element is. But in this case, this find rotation point function is looking to do something a little bit different, right? We don't have a specified target element that we're looking for. We're looking for some element that matches some criteria. So the question then becomes, what can we compare? Once we've calculated the midpoint and accessed the midpoint element in the array, what do we compare that against? So I'm going to go ahead and suggest we can compare the midpoint element against the first element in the array, right? And so if we go ahead and do that, and let's go and look at, if we're talking about this input up here, the midpoint element in this case actually is going to be the 49 right in the middle. And so what we're going to do is we're going to take this 49 and we're going to compare it to the 19. Okay, and so if we go ahead and do that, take the midpoint element and compare it to the first element in the array, we'll see that, hey, 49 in this case is greater than 19. And if that's the case, if 49 is greater than 19, then logically what that tells us, or what we can assume then, is that everything from 49 to 19 is sorted, right? Because again, we're automatically assuming that the array is almost sorted except for the fact that there's a rotation point and some things have been shifted. But other than that, it's completely sorted. So again, if we see 49 greater than 19, then that tells us then that the rotation point actually cannot be in this left subarray. It's got to be in the right subarray somewhere over in here, in these highlighted elements. Okay, and so from that point, if we continue and basically recurse and do that same thing all over again, find the midpoint, and in this case that's going to be the 10. And now let's go ahead and compare 10 against the first element, 19. All right, so same first element over here. If we compare 10 against 19, now 10 is smaller. And because 10 is smaller, that tells us now that the rotation point is somewhere in here, in between 49 and 10. So now we've narrowed our search down to here, and we go ahead and do the same thing again. Now the midpoint element in this range is the 5. We'll take the 5, compare that against the 19. 5 is still less, so that allows us to cut out the 6 and the 10, and now we've narrowed our range down to these two. The midpoint now here is the 2. 2 is less than 19. And so at that point, we can throw out the 5 because we're going left again. Okay, we can throw out the 5, and now we're down to this point. And this is where we get to the base case for this find rotation point function, right? The base case here is going to be when we get down to 2 elements. We're going to get down eventually to a range of 2 things, one right next to the other. And when that happens, then that actually, we'll know then that the smallest element, the rotation point, will sit right between the 49 and the 2, which it does. And so at that point, we can return the right index, because that'll be the starting point of the new sorted array in this case. So if we go ahead and write that down, we compare the midpoint element against the first element in the array. Let me go ahead and write our base case up here that we were talking about earlier. So the issue is only just 1. But the base case in this case is going to be when we've narrowed our search down to 2 elements that are right next to each other. we'll say in that case, return the right element of the 2. Because again, that's the starting element of the second sorted subarray. Okay, so that's our base case. We do the comparison over here, and then we'll say if array mid of is greater than, let's say, the first element, then we go we go right. Else if array mid is less than the first element, we go left. And then we'll also check for our base case as we're looping through. Sorry, I should say also then that we'll say while left again is less than right. But here it's not going to be less than or equal, it's just going to be left and right, because actually we're not looking in this case to have left and right overlap, because we are assuming that there is indeed a rotation point here, and so we're not having a second base case where we've overshot left and right and we're returning -1, because we're always making the assumption here that there is always a rotation point. So we're not actually going to have a base case that's checking for if left and right have overshot. But anyways, over here we'll check for our base case. If we have 2 elements right next to each other, return the right element. Okay. So again, that's going to be our what. So let's go ahead now and write out our how. Okay, so what I'm going to do, let's start up here. I'm going to store a variable to our first element, and then we'll also have a left, which is going to be 0, and a right, which will be length of array -1, because those are not passed in to this array over here, because it's not needed. We can just go ahead and initialize them inside the function itself. And then we'll go ahead and say while left is less than right, calculate our midpoint. Add that, calculate our midpoint. So mid will be, we'll say the same formula as what we had in the binary search function. And then we'll say, hey, if array mid is greater than first, in this case, we're going to do this one actually iteratively. So what we're going to do is we're just going to update left. If we update left to be mid, that means then that the left boundary has been moved up and we're disregarding the left subarray that we're tossing out. And then let's just say else in this case, well, let's make it a little more explicit. Else if array mid is less than first, we go right. So here it will be right will be equal to mid. Okay, now we're going to check for our base case for when we've narrowed it down into 2 elements. And the way we can check for if we've narrowed it down into 2 elements, we can just say, hey, if left plus 1 matches right, well, we can just return right in that case. All right, so that's our find rotation point. Again, separated the what and the how, and because of the fact that we just relegated this to its own function, when we were working on it, we just had to think about this problem right in front of us, implementing this function, and again, not having to worry about, details about the shifted binary search function or the binary search helper function that we worked on up here. We just were focusing on the logic for this problem and only this problem. And And now that we've finished that, we can go ahead and do a little bit of testing. So is this? I'm thinking it's complaining about okay, let me change this a little bit. I think it's complaining about some white space. So let's just break out of that, and then here we will return right. Yeah, I think it's complaining about some kind of white space stuff. Okay, good old Python. So if we go ahead and give it this array, and then call our find rotation point on this array, commented that one out, and then run this, we're expecting to find 0, 1, 2, 3, 4, 5, 6. We're expecting to find 8, the index where this 2 is. So we go ahead and run that. And yep, okay, debug output over here, we get 8. So that returns the correct output. So that seems like it's working as expected, at least for this particular case. Okay, but at least we have a little bit of peace of mind that probably for the most part these two functions are working, which is really nice then. So we can go ahead and now give the appropriate parameters to these helper functions. So array for the find rotation point function, array and target for this binary search, and because it's the left one, we're going to give it 0, as well as smallest index -1. So up to the element right before the smallest index, right before the 2, so up to that 49. Here it's going to be array target smallest index for the left boundary, and then length of the array on the right for the right boundary. And now at this point, we've finished officially the shifted binary search function, and let's go ahead and test that now. Camel case. So let's give it this same array up here. Let's look for the 33, run that. Shift. Yep, okay. Okay, so yep, 3, debug output 3. Okay, so that seems to be working, and then if we go ahead and give it a 100, should go ahead and give us a -1 now. Okay, -1 there. Okay, cool. So that's evidently mostly done. I'm not passing one of these tests. And for the so something there is not. Okay, anyways, well, I'm not gonna spend time debugging that. The biggest takeaway I wanted to introduce in this video is the flow, right? Because I'm looking to address specifically students not submitting particularly clean or particularly easily readable code. And that's why I recommend this particular flow, because it actually yields clean, modular, and easy to read code kind of just off the bat, right? So one thing that I've seen that students typically, when they submit their code, or at least when I see students work on a problem, right? So I think generally speaking, people will kind of start on the details kind of too quickly right off the bat. A lot of people I see will start working on the how kind of immediately, or very, maybe perhaps too soon, right? So one thing I would advocate strongly is to, again, separate the what and the how and finish thinking about the what before you start thinking about the how. Because that makes the steps much clearer as to what you actually need to do before you even get to the point where you're thinking of details, right? It's nice to have that overall scaffolding and overarching idea of what you're going to be doing at a high level to solve the problem before you start digging into the details, right? Which is one thing I'd strongly advocate for. The other being breaking up distinct pieces of logic into their own separate functions, and then when you do that, using those function stubs as bookmarks to then remind you to come back to those later, so that when you do come back to them later, you are only working on that particular problem right in front of you, right? One thing that I see that's pretty common in submissions on this assessment is kind of, I'm not necessarily going to say messy code, but code where all the logic is just smushed together into a single function. And that's not helpful to the person who's actually trying to read and interpret the code, because it's not as modular, and there's a lot more logic kind of all in one place that needs to get parsed through, right? It's a lot easier. Well, correct me if I'm wrong, but I think it's a lot easier to actually read through just something like this, where if you're looking at this, there's comments indicating, personally, I wouldn't actually have all of these comments in the finished product. I would just try to have comments where something is perhaps, some line of code perhaps doesn't actually speak for itself, but this is more for illustration purposes to illustrate the actual flow itself. But point being is it's a lot easier to parse something like this, some code like this, where someone reading this code can just look at this and be like, oh, there's this function here called find rotation point. I'm not entirely clear on the details, but I would assume that that's somehow figuring out the rotation point given some input array, right? So to someone reading that, they're not going to necessarily, they don't have to think about the details of that right then and there, right? Which is nice, because then for the reader of the code as well, they can move on to looking at this function after they've parsed through everything else. And so they don't need to worry about the details here right at the moment, right? So it helps you think about the problem, and it also helps the person who's reading your code and trying to parse and understand how your code works. It helps them to understand it much more quickly and read through it much more easily as well. So it kind of kills that bird as well. And of course, just having modular code at the end of the day is overall just a lot easier to parse, because different functions handle things distinctly. And again, correct me if I'm wrong, but I think that makes code easier to read. Some more benefits, because I'm just going to keep spouting on them, because I think there are a bunch of benefits to doing to structuring your workflow when you're working on a problem this way, right? As we saw earlier, it made things easier to test, right? Again, because our code was structured modularly, when we just hashed out a single function, we could then go ahead and test that right then and there, and at least get a little bit of peace of mind that, hey, this function is working to some degree, right? So in order to debug this problem down here, if I were to go ahead and actually debug that, it gives me some idea that, maybe, probably most likely, there's a problem in the shifted binary search function itself, because of the fact that we tested both the find rotation point as well as the binary search functions. We tested those, and because those seemed like they were working correctly from our limited testing, maybe that points us to an error in the shifted binary search function that we are overlooking. Right? When our code is modular like this and we can test individual pieces, that gives us more information as to, hey, maybe points me in the right direction as to where the problem is. And then the last benefit of this workflow that I'm going to also mention is that, well, it actually makes it a lot easier to reason about the runtime complexity of our finished implementation. Right? Because if we looked at our finished implementation here for shifted binary search, well, we call a helper function here, we call 2 more helper functions here, and then other than that, we did a couple of if-else checks, which just returned variables. So really all of this stuff here, this is all constant, as well as far as the amount of work all this stuff does is regarded. So everything down here is O of 1 constant times. So if we want to evaluate our shifted binary search, we just need to go ahead and evaluate the runtimes of our find rotation point as well as our binary search. And so now we can just go ahead and look at that on its own. With a binary search, I mean, if we go ahead and implement a binary search correctly, as we've done here, then the runtime will be an O log of n, because we are on every iteration halving the array on every single iteration step. Every single recursive call of the binary search function, this is getting called with half the size of the array if it's the previous. So that goes ahead, that gives us a log of n runtime. And then in this case as well, we are halving the input array on every single iteration step, so that would give us a log n if we did that correctly, which I'm going to go ahead and assume that we did here. So then, now that we've determined those two, over here now when we want to go ahead and ascertain the runtime for the overall shifted binary search, again, we just determined that find rotation point exhibits a log n, binary search over here exhibits a log n, and then there's another binary search over here exhibiting another log n. And because all of these log n's, none of them are nested within one another, they're all just at the same scope level, the overall runtime then would be given as log of n plus log of n plus log of n. So technically coming out to O of 3 times log n, because there's 3 of those, which we would go ahead and simplify down to an overall runtime of log of n. So again, arising due to the fact that our code is very modular, we would just kind of, as far as ascertaining runtime is concerned, for the most part, we can go ahead and look at each of these helper functions individually to figure out what their runtimes are. Again, stemming from the fact that our code is modular, that then helps us to figure out the runtimes of these, which then gives us the overall runtime for the function. So at the end of the day, I think the biggest win here is that we get clean code without having to do any cleanup, right? I think the more general flow, the more typical flow that I've seen for students as far as writing clean code is they'll write out their solution, they'll test it, see that it's working from the tests, and then what they'll do at that point is, you know, hey, if I have time, I should go ahead and clean this up. Right, and then maybe at that point you'll go ahead and do some refactoring of the code. And when you go with that flow, the cleaning up feels like a chore because you're already finished and you're like, okay, I guess I'll clean up the code at this point now, even though I've got it working, right? It feels like a chore and it feels a little bit tedious. So I would strongly advocate for kind of flipping that model on its head and be like, hey, let's think about our problem in a logical and modular fashion from the get-go, which then translates to us writing clean modular code from the get-go. And so once we get it working, there's no cleanup that we have to do. Our code is already well organized and modular, and we don't need to spend any extra time at the end to kind of clean it up and get it looking nice and readable for another human to read. It's already like that from the get-go, which then comes back, which all kind of circles back to the fact that we kind of structured our flow in an organized fashion, and that's how we got an organized solution and implementation at the end of the day. So wrapping that up, that's kind of the main takeaway that I wanted to address in this video. And if you have any comments or questions on anything further that about anything I was talking about in this video, go ahead and DM me. But then other than that, I'm going to go ahead and sign off here, and I will see you all later.